Something out there is heavy enough to pull our entire galaxy off course, and no one has ever seen it. Not hidden by distance, hidden by direction. It sits behind the crowded center of our own Milky Way, in the one stretch of sky our telescopes cannot see through. And for almost 40 years we have known it only by the way everything around us leans toward it. We drew a border around the region it commands and gave it a name, Laniakea. But the more carefully we measured, the stranger the pull became. Tonight we trace the hidden mass we can weigh but never look at, the rival giant that may be winning a tug of war against it, and the discovery that whatever holds us was never holding us at all. If these quiet journeys help you drift off, a like and a subscribe lets the next one reach you while you sleep. And I read every comment. So tell me what stayed with you tonight and what I can make softer next time. But before we chase the thing pulling us, sit with the part that should frighten us more. You are moving faster than any machine ever built, straight toward it, and every nerve in your body swears you are lying perfectly still. The Milky Way is moving through the universe at roughly 1 1/3 million miles per hour. In the units most of the world uses, that is about 600 kilometers every second. This is not the Earth circling the Sun, which is its own slower motion. It is not the Sun circling the galaxy, slower still. This is the whole galaxy, every star inside it, the Sun and the Earth and the bed you are lying in, all of it sailing one direction at a speed that would carry you coast to coast across a continent in about 4 seconds. And you have never felt a thing. Your body never measures speed. It measures change in speed. A nerve inside your ear answers only to acceleration, to the push of speeding up, the drop of slowing down, the lean of a turn. Hold a steady line at a steady pace, and that nerve goes quiet. You already know this, even if you have never named it. On the smoothest flight you have ever taken, 500 miles an hour, the cup of water on your tray sitting flat and still, you could close your eyes and lose all sense that you were moving at all. Our galaxy is that cabin, scaled past imagining, and nothing inside it ever hits turbulence. We cannot point a speedometer at empty space. Speed only means something measured against a reference. And out here there is no roadside, no mile markers, no ground sliding past a window. Every galaxy we might compare ourselves to is also moving, also being pulled, also carried off in its own direction. For a long stretch of the last century, this looked like a closed door. We had nothing fixed in the universe to set our motion against. The oldest light in the universe gave us the roadside we lacked. It fills the entire sky, every direction you could turn your head, a faint glow left over from when everything was young and unbearably hot. That light has been traveling almost the full age of the universe, cooling the whole way, until now it rests just a few degrees above the coldest temperature anything can reach. It surrounds us evenly, like the warmth still held in an oven long after you switch off the heat. Because it comes at us from everywhere at once, it hands us a kind of stillness we can finally measure ourselves against. Read that ancient light in every direction, and a sitting still universe would show you the exact same temperature everywhere. Ours does not. One patch of sky reads a touch warmer, and the patch directly opposite reads a touch cooler. That pattern says nothing about the light and everything about us. We are rushing toward the warm side, and the light coming at us from ahead piles up and shifts warmer, the way a siren climbs in pitch as it races toward you. The light falling behind us stretches and cools, the way that same siren drops as it passes and pulls away. Measure how big that warm to cool difference is, and it gives you the speed. 1.33 million miles per hour, about 600 kilometers per second, aimed at one specific point in the sky. It took me a long time to make peace with the pairing underneath that. The most violent motion your atoms will ever take is also the quietest thing you will ever do, and both of those are true in the same breath. There is no contradiction hiding in it. We are simply instruments built to feel change, and a steady fall gives us nothing to feel. Fall is the right word, and it is the one to carry into everything ahead. Nothing is propelling us. No engine, no thrust, no chosen heading. We are falling, in the plainest way gravity allows, drawn toward a concentration of mass, the way a dropped stone is drawn toward the floor. An astronaut floats inside a spacecraft for exactly this reason, while she and the ship together plunge around the Earth at thousands of miles an hour. When gravity is the only hand on you, nothing is left to press against your nerves, and the wildest motion of your life slips by as perfect calm. The galaxy is in free fall. Your bed is in free fall. You are in free fall as you listen, and it feels like lying still, because lying still is precisely what free fall feels like from the inside. The universe is expanding. Space itself stretches, carrying distant galaxies apart from one another, and that stretching shows up as motion too. So every galaxy we watch is moving for two reasons braided into one measurement. Part of it is just the broad swelling of space, the tide that lifts every boat together. And part of it is a real, local pull, a current running through that tide, gravity hauling it towards something in particular. That second part, the true travel through space rather than the stretching of space, carries a name. Astronomers call it peculiar velocity. Our 600 kilometers a second belongs entirely to that second kind. It is not the universe expanding. It is us, leaning, pointed, falling toward a destination through a universe that keeps trying to carry us the other way. We can measure our speed. We can read our heading in the warm patch of that ancient light. We can even peel the real fall away from the stretching of space. But follow that heading outward, expecting to find whatever does the pulling, and you run straight into a problem no better telescope can fix. The thing we fall towards sits in the one stretch of sky we are physically unable to see into. And the closer astronomers looked at the galaxies around us, the clearer it became that our galaxy is not falling alone, or even mostly on its own account. We move as part of something far larger, sorted into a vast procession of galaxies all leaning the same way, a structure nobody had drawn yet, because nobody had thought to look for a thing made entirely of motion. So the first question is not, what is pulling us? It is what we are already a part of, if the home we belong to has no wall, no surface, and no center where any of us could ever stand. For most of the last century, we mapped our region of the universe as several separate superclusters, each with its own name and its own borders. The one we live in was called the Virgo Supercluster, a collection of thousands of galaxies spread across roughly 110 million light-years, with the Milky Way far out toward its outer edge. In other directions, we charted other superclusters, the Hydra Centaurus region, the Pavo Indus stream, a heavy concentration of galaxies toward the constellation Centaurus. We listed them as separate structures, each a distinct member of the cosmic catalog, each ending where the next began. Those borders came from a single kind of measurement. For decades, the way we decided where one supercluster stopped and another started was to count galaxies by position, marking where they crowded together and where they thinned out. Wherever galaxies gathered densely, we drew a structure. Wherever the count dropped, we drew a boundary. That method records one thing only, and it records it well, which is the location of matter at this moment. What it cannot tell you is where any of that matter is going. Position is a still frame. It holds no information about motion, and motion is the thing that turned out to matter most. Every galaxy carries two kinds of movement mixed together: the smooth expansion of space that we set aside earlier, and the real fall caused by gravity, the part we called peculiar velocity. Strip away the expansion, and what remains is the direction each galaxy is actually being pulled. Do this for thousands of galaxies across our region, and a pattern appears that position alone had completely hidden. The galaxies of Virgo, the galaxies of Hydra Centaurus, the galaxies in the Pavo Indus stream, and the dense crowds toward Centaurus are all moving the same way. They are all falling toward one common point. Their flow lines, the paths their motion traces, do not stay inside the old borders. They cross them, and they converge. In the year 2014, a small team carried out exactly this measurement, using the velocities of thousands of galaxies to find where all the flow lines led. What they found erased the borders we had trusted for generations. Our Virgo supercluster is not a structure in its own right. It is one component of something far larger, a single region defined by the fact that everything inside it is falling toward the same gravitational focus. The Hydra Centaurus region, the Pavo Indus stream, the Centaurus concentration, and our own Virgo arm are not four neighbors. They are four parts of one structure, and the only thing that defines its edge is where the flow lines stop converging toward this focus and begin converging toward a different one somewhere else. The boundary is not a place where matter ends. It is the surface where one direction of falling gives way to another. What should unsettle you here has nothing to do with how large the structure turned out to be. No new matter was found between the old superclusters. No hidden mass appeared at the borders. No missing galaxies lit up in the gaps. Nothing in the physical universe was added or moved. Every galaxy stayed exactly where we had always known it to be. The only thing that changed was the question we asked, position replaced by motion, and that single change enlarged the place we call home from one supercluster to a structure containing 100,000 galaxies. We did not find a bigger universe out there. We found that our address had always been larger, and that we had been writing it down wrong because we had been measuring the wrong quantity. That is the detail that stays with me long after the numbers fade. The size of the structure is not what changed. Our understanding of what counts as a structure is what changed. For most of the history of this science, we assumed a cosmic structure was a place where matter gathers. The motion measurements forced a different definition, one where a structure is not a gathering of matter at all, but a shared destination, a set of galaxies bound together by nothing except the fact that gravity is pulling all of them toward the same point. Take away that shared fall, and there is no wall, no surface, no material thread holding these galaxies as one. You belong to a structure whose entire substance is a direction, the direction we are all moving together, toward a place none of us chose and none of us will reach. If everything in our structure is falling toward one focus, then somewhere at that focus, there must be a concentration of mass large enough to govern the motion of 100,000 galaxies across roughly 500 million light-years. A mass with that much gravitational authority should be the most obvious object in our sky. It should dominate every map. It should be the first thing any of us learn to find. It is none of those things. We have measured its pull for close to 40 years. We have traced the flow of galaxies falling toward it. We have calculated how strongly it bends the motion of everything around us. In all that time, no one has ever seen it directly, not once, not in any telescope ever built. The reason is not distance. And it is not that the object is faint or strange or hiding by some deliberate trick of physics. The reason is built into the structure of the galaxy we live inside. The focus that organizes our entire region lies in a direction the Milky Way itself blocks from view. Between us and the center of everything we belong to stands the thick, crowded disk of our own galaxy, dense with stars and dust, and it sits almost exactly across the line of sight we would need to look along. The most important object in our cosmic neighborhood is hidden, not by being far away, but by being directly behind the one part of the sky we can never see through. So before we can ask what that mass actually is, we have to face why our own galaxy refuses to let us look at it. What exactly is standing between us and the center of the structure we call home, and how have we managed to weigh something for 40 years that no human eye has ever been allowed to see? The Milky Way is a flat disk of several 100 billion stars, and we live inside that disk, embedded in its plane rather than floating above it. From where the Earth sits, that disk wraps all the way around us as a band of crowded starlight, the pale river you can still see on a dark night far from city lights. Along that band, the stars are packed densest and the clouds of gas and dust are thickest. Dust is the problem. Interstellar dust absorbs and scatters visible light, and along the plane of our own galaxy it piles up so deeply that it forms a nearly continuous screen. Anything sitting behind that screen, out beyond our galaxy, has its light swallowed before it can ever reach us. Astronomers gave this blocked band a name that says exactly what it does. They call it the zone of avoidance, because for a century the galaxies we cataloged seemed to avoid it, vanishing wherever the band crossed the sky. The galaxies were never really avoiding anything. They were there the whole time, behind the dust, their light simply extinguished before it arrived. The zone of avoidance covers a wide strip of sky, and depending on how you count, it hides somewhere around a fifth of the entire universe beyond our galaxy from our view in ordinary light. For most of the history of this science, that was a frustrating but tolerable gap. A fifth of the sky is a great deal to lose, but the universe is roughly the same in every direction, so we assumed we were not missing anything we could not also find elsewhere. That assumption held until we measured the motion of our own galaxy and discovered that the thing pulling us, the focus that all those flow lines pour toward, sits almost exactly inside the blocked band. Of all the directions the mass could have hidden in, it chose the one we cannot see. The focus of our region lies toward the constellations Norma and Centaurus, low in the southern sky, in a stretch that runs right through the thickest part of our galaxy's plane. This is the part that should sit strangely with you. The single most influential concentration of mass in our entire neighborhood, the gravitational center of everything we belong to, is positioned behind the one screen our eyes were never able to pierce. We did not choose to be blind to it. The geometry of where we live chose that for us. We happen to sit inside a galaxy whose own body falls across the line we would need to look along, and so the most important object in our sky became the one object we were structurally forbidden to see. For decades, that left us in a position that sounds almost impossible to defend. We were certain something enormous was out there, pulling our whole region toward it, and we could not point a single telescope at it and see anything at all. Everything we knew about it, we knew indirectly. Through the fall of the galaxies we could see on either side of the blocked band. By measuring how thousands of those galaxies were leaning, we could calculate where the pull was coming from and roughly how strong it had to be, without ever laying eyes on its source. In the late 1980s, a group of astronomers studying these motions named the hidden mass the Great Attractor, and the name was never poetry. It was a plain description of the only thing they could measure, which was that something in that direction was attracting everything, and it was great. Knowing a thing exists and being unable to look at it is a difficult state for any science to sit in. So, the work of the last few decades became a long effort to find a way through the screen, not by removing the dust, which is impossible, but by looking in kinds of light the dust cannot stop. Dust blocks visible light efficiently, but its grip weakens as you move to longer wavelengths. Near-infrared light, just beyond what your eyes can see, slips through the dust far more easily than visible light does, and surveys tuned to it began to recover galaxies that had been invisible inside the band. Radio waves pass through almost untouched. Neutral hydrogen gas, which fills most galaxies, gives off a faint radio signal at a wavelength of about 21 centimeters, and that signal crosses the dust as though it were not there, letting us detect galaxies in the zone of avoidance by their gas alone. X-rays revealed something else. The hot gas that pools inside massive galaxy clusters, glowing in a kind of light that pierces the band and marks where the largest concentrations of mass are hiding. One astronomer in particular, René Kron-Korteweg, spent years patiently surveying this forbidden strip, counting galaxies that no one had ever recorded because no one had been able to see them. Through that work, the region behind the band slowly came into focus. Near the heart of the Great Attractor sits a massive cluster of galaxies called the Norma Cluster, a dense gathering of hundreds of galaxies that had been hiding behind the dust the entire time. For the first time, we were no longer only feeling the pull, we were beginning to see, dimly and in borrowed wavelengths, the mass responsible for it. After a century of avoidance, the galaxies in the blocked band were finally being named. When astronomers added up all the mass they could now detect behind the band, the Norma Cluster and the galaxies around it, they found something that did not balance. The visible mass in that direction, real and substantial as it was, did not appear to be enough to fully account for the pull we measure. The Great Attractor was supposed to be the answer, the destination at the bottom of the slope. Instead, the closer we looked, the more it seemed to be only part of the answer, a concentration of mass that is genuinely there and genuinely pulling, yet not heavy enough on its own to explain why our entire region is moving as fast as it is. Something further away, something even larger, appears to be adding to the pull from beyond. We began this part blind to the center of our own structure, unable to see the mass that organizes our motion. We found ways to see partway through the screen, and we located a real cluster of galaxies sitting where the pull pointed. But instead of resolving the question, that discovery sharpened it, because the thing we finally saw turned out to be too small to be the whole cause. We can now see most of what is pulling us. We simply cannot find enough of it. So the question is no longer only why we are blind to our own center. The question is what lies beyond it, far past the Norma Cluster, in the same direction but deeper, heavy enough to be pulling not only us but the Great Attractor itself towards something larger still. Far beyond the Norma Cluster, in almost exactly the same direction we have been straining to see, lies a concentration of galaxies so large that it changes the entire shape of this story. It is called the Shapley Concentration, and it sits roughly 650 million light-years away from us, more than twice as far as the Great Attractor. At that distance, its light takes 650 million years to reach us, which means we see it as it was long before the first complex life appeared on Earth. And what we see, even across that gulf, is the densest gathering of mass in this entire region of the universe. To understand why it matters, you have to hold its scale next to things we have already named. Our own local group, the small collection of galaxies that includes the Milky Way, contains only about a few dozen members, most of them faint and small. The Norma Cluster, the heart of the Great Attractor, gathers many hundreds of galaxies into a single dense knot. The Shapley Concentration holds something on a different level entirely. More than a dozen massive galaxy clusters, each one rivaling or exceeding Norma, packed close together into one immense complex. Tens of thousands of galaxies are bound up in it. Nothing else in the nearby universe comes close to that much mass collected in one place. When astronomers look for the single heaviest structure within roughly 1 billion light-years of us, the answer keeps coming back to Shapley. We have known about it, in a faint and incomplete way, for a long time. In the year 1930, the astronomer Harlow Shapley noticed an unusual cloud of galaxies in the direction of the constellation Centaurus, a richer crowding than the surrounding sky seemed to explain. He recorded it as a curiosity, a notable cloud, and the full meaning of what he had found stayed hidden for decades. The instruments of his time could not measure how far away those galaxies were or how much mass they truly represented. It took most of the following century and far better surveys to reveal that Shapley's curious cloud was the largest single concentration of galaxies in our part of the cosmos. He had glimpsed the heaviest thing in our neighborhood, and neither he nor anyone else realized for years just how heavy it was. From our position, the Shapley Concentration lies almost directly behind the Great Attractor, deeper along the same line of sight. Both of them are in roughly the same direction, the Norma region in the foreground, Shapley far behind it. This means their gravity does not pull us in two different directions that we could separate easily. They pull us the same way, one nearer and lighter, one farther and vastly heavier, and the motion we actually measure is the combined result of both pulls added together. When we feel our region falling toward Norma, part of that fall is Norma, and part of it is the far greater mass lying beyond Norma, reaching across hundreds of millions of light-years to add its weight to ours. The visible mass of the Great Attractor was real, but it was not enough on its own to explain how fast we are moving. Gravity weakens with distance, growing weaker as the square of how far away the source is. So you might expect something 650 million light-years away to be far too remote to matter. For most objects, that would be true. But Shapley is so extraordinarily massive that even with its pull weakened by all that distance, it still contributes a real and measurable share of our motion. The Great Attractor was never the whole answer. It was the nearer, more visible piece of a pull that reaches much deeper into the universe than we first believed. Some analyses give the Great Attractor and its immediate surroundings the larger share of our motion. Others find that a substantial fraction, in some studies approaching half, comes from beyond the Great Attractor, from Shapley and the mass concentrated around it. The disagreement is not carelessness. It comes from how hard the measurement is, because both sources lie in nearly the same direction, and because measuring exact distances to galaxies hundreds of millions of light-years away still carries real uncertainty. When two masses pull from the same line of sight, separating how much each one contributes is one of the genuinely difficult problems in this field, and the numbers shift as the surveys improve. What nearly everyone agrees on is the part that matters most here. The pull on us does not stop at the Great Attractor. It extends far beyond it. That agreement carries an implication that reorders everything we have built so far. If Shapley is pulling us from beyond the Great Attractor, then it is also pulling the Great Attractor. The Norma Cluster, the mass we spent a century trying to see, the focus we said our entire region was falling toward, is itself falling. It is sliding in the same direction we are, drawn toward the heavier concentration behind it. The thing we are falling toward is not standing still at the bottom of a slope, waiting for us. It is moving, leaning, falling alongside us, towards something larger than itself. We measured our galaxy's motion and found it falling toward the local group's surroundings. We looked further and found that whole region falling toward the Great Attractor. We looked further still and found the Great Attractor falling toward Shapley. Every time we believe we have located the bottom, the thing we found turns out to be in motion too, pulled by something heavier and deeper than itself. And the honest truth is that we do not know with certainty that Shapley is the end of that chain. It is the largest mass we can confidently identify nearby, but whether it is the true floor of the slope or just the deepest point we have managed to measure so far remains an open question. So you might reasonably expect this part to end by pointing even further out, toward some still larger mass beyond Shapley. But the next discovery does not work that way, and it is stranger than anything we have met yet. When astronomers built their most careful map of what moves our region, adding up the pull of the Great Attractor and the deeper pull of Shapley, they found that the pulling masses alone still did not fully describe our motion. Part of where we are going seems to come not from anything pulling us toward it. It seems to come from a place that is pushing us away. So the question is no longer only what is pulling us or how far the pull reaches. The question is how an almost empty region of the universe, containing very little mass at all, could be shoving our entire neighborhood across hundreds of millions of light years as though emptiness itself had a force of its own. In the year 2017, a group of astronomers mapping the motion of our region found that part of where we are going points away from a vast stretch of the universe that is nearly empty of galaxies. This region lies on roughly the opposite side of the sky from the Shapley Concentration, and it contains far fewer galaxies than an average patch of the universe should. They called it the Dipole Repeller, and the claim attached to it sounds, at first, like a contradiction. A place with almost nothing in it appears to be helping drive the motion of 100,000 galaxies, our own included. Your instinct is right to resist that. Emptiness has no mass. A region with very little matter in it has very little gravity, and a thing with very little gravity should not be able to push anything anywhere. Nothing cannot exert a force. So if a nearly empty region is influencing our motion, either we have the physics wrong, or the word push is hiding something more subtle than it first appears. It is the second one. The push is real. Our motion away from that region is genuine, but the cause is not a force coming out of the emptiness. The cause is everything else. To see how that works, picture the gravity acting on our region from every direction at once. The universe, on the largest scales, is filled with matter spread fairly evenly, galaxies and clusters scattered in all directions around us. Each of those masses pulls on us. The mass to our left pulls us left, the mass to our right pulls us right, and when matter is spread evenly all around, those pulls very nearly cancel each other out. The pull in one direction is balanced by an equal pull in the opposite direction, and the net result is close to nothing. This balance is the quiet default of the cosmos. When mass surrounds you evenly, you feel pulled in every direction, and therefore pulled, on balance, in none. Now take away the matter on one side. Carve out a region where galaxies are sparse, where there is far less mass than average, and place it off in one direction. The pull from that direction weakens because there is less there to do the pulling. But the pull from the opposite direction, where matter is still plentiful, does not weaken at all. Suddenly the balance is broken. You are still being pulled normally on one side, and pulled less than normal on the other, and the difference between those two leaves you drifting toward the fuller side and away from the emptier one. That drift is exactly what we measure. We move away from the empty region, not because the emptiness is pushing us, but because the matter on the far side is no longer being counterbalanced. The push is the shape of an absence. It is what a missing pull feels like. This is why they called it a repeller, and why the full pattern is called a dipole. The Shapley Concentration, the enormous mass we met in the last part, sits on one side of us and pulls us toward it. The Dipole Repeller, the great underdense region, sits on roughly the opposite side and effectively pushes us in the same direction, away from itself. The two work together. A pull from ahead and a push from behind, both urging our region the same way, combine into the dominant pattern of our motion. That is what the word dipole means here. Two poles of a single flow, one a surplus of mass drawing us in, the other a deficit of mass letting us slip away, and our galaxy riding the line between them. You cannot point a telescope at a void and photograph absence. The dipole repeller was found a different way, by reconstructing the motion of thousands of galaxies across our part of the universe and building a full map of how everything is flowing. When that map was complete, it showed the flow lines streaming away from one particular region as clearly as they streamed toward Shapley on the other side. The emptiness announced itself, not by anything it contained, but by the way everything around it was moving. We detected a hole in the universe by watching how the matter near it leaned away. It is worth being careful about what this region actually is, because the language can mislead. The dipole repeller is not a place of perfect, absolute nothingness. It still contains some galaxies, some matter, scattered thinly through it. What makes it matter is that it holds significantly less than the cosmic average, and in a universe where balance depends on mass being spread evenly, even a moderate shortfall in one direction is enough to tilt the motion of everything nearby. The exact depth of that shortfall, and exactly how much of our motion it accounts for, are still being refined as the velocity maps improve. This is a result built from reconstructing a flow, not from a direct image, and the reconstruction carries real uncertainty. But the basic finding has held up. Part of our motion is shaped by where matter is not. That idea is the one I find hardest to set down, and the most quietly profound thing in this entire story so far. We began by asking what is pulling us, as though motion in the universe were only ever about being drawn toward mass. The dipole repeller shows that this was only half the picture. Our path through the cosmos is shaped just as much by absence as by presence, by the empty regions we are sliding away from, as by the dense regions we are falling toward. The voids are not passive gaps between the real structures, they are participants. Where the universe chose to put nothing has steered our galaxy as surely as where it chose to put everything. Bring the two sides together, and the motion we have been tracing finally has a shape. The pull of the Great Attractor and the deeper pull of Shapley draw us one way. The push of the dipole repeller, the unbalanced absence behind us, drives us the same way. Added together, these are enough to account for most of the roughly 600 kilometers per second that carries our entire region across the universe. After decades of work, we can finally name the major forces moving us, the masses ahead and the emptiness behind, and watch them combine into the single quiet motion you have never felt. But every part of what I have just told you rests on one assumption we have not yet examined, and it is the assumption the entire field is built on. Every claim about pulls and pushes, every number, every map of the flow, depends on our being able to measure how a galaxy is truly moving through space. And that is far harder than it sounds, because the universe is expanding, and the stretching of space disguises itself as motion in every measurement we take. So before we can trust a single one of these numbers, we have to answer a deceptively simple question. How do you separate a galaxy's real motion from the stretching of space that is carrying it along when both of them look almost exactly the same when they reach us? Almost everything we know about a distant galaxy arrives in a single thin stream of light, and the most important thing we read in that light is how much its colors have been stretched. Every galaxy is full of specific elements, hydrogen, calcium, and others, and each element absorbs and emits light at exact, known wavelengths that act as fixed markers. When we spread a galaxy's light into a spectrum, we find those same markers, but shifted. Every one of them move toward the red, longer wavelength end by the same proportion. That shift is called redshift, and measuring it is one of the most precise things we can do in all of astronomy. We can read how much a galaxy's light has been stretched to a tiny fraction of a percent. The trouble is not measuring the stretch. The trouble is that two completely different things cause it, and they arrive blended into the same number. The first cause is the expansion of the universe itself. As light travels across space toward us, space is stretching the whole time it is in flight, and that stretching pulls the light's wavelengths longer, redder, by the time it arrives. The farther the light has traveled, the more stretching it has been through, and the more redshifted it becomes. This kind of redshift has nothing to do with the galaxy moving. It is the space between us and the galaxy growing while the light crosses it. The second cause is the galaxy's own motion through space, the real fall we have been tracing this whole time, its peculiar velocity. If a galaxy is moving toward us, its light is compressed, slightly bluer. If it is moving away, its light is stretched, slightly redder. Both causes do the same thing to the light. Both shift the markers, and when the light reaches our instruments, there is nothing in the redshift itself that tells us how much came from expansion and how much came from real motion. When we say our region is falling toward Shapley or sliding away from the Dipole Repeller, we are talking about peculiar velocity, the second cause, the real motion. But every galaxy we measure hands us a redshift that is mostly the first cause, the expansion, with the real motion buried inside it as a small extra contribution. To study the flow, we have to pull those two apart. We have to take the total redshift we measured and somehow subtract out the part that is only the stretching of space, so that what remains is the galaxy's true motion. And to do that subtraction, we need to know one more thing about the galaxy that the redshift alone cannot give us. We need to know how far away it is. The reason distance is the key comes from a relationship discovered nearly a century ago. The expansion of the universe is orderly. A galaxy twice as far away is carried away from us twice as fast by that expansion, 3 times as far, 3 times as fast, in steady proportion. The rate works out to roughly 70 kilometers per second for every megaparsec of distance, and a megaparsec is about 3.25 million light-years. So for every 3.25 million light-years farther out a galaxy sits, the expansion alone carries it away about 70 kilometers per second faster. This is the tool we needed. If we know a galaxy's true distance, we can calculate exactly how much recession the expansion by itself should produce, with no real motion involved at all. Now the separation becomes possible, and it comes down to a single subtraction. Measure the galaxy's total recession from its redshift. Measure its distance independently. Multiply that distance by the expansion rate to find how much recession the stretching of space should account for. Then subtract that predicted expansion from the total you measured. Whatever is left over is the peculiar velocity, the real motion caused by local gravity, the number we actually care about. Picture a galaxy whose distance tells us that expansion alone should be carrying it away at 7,000 kilometers per second. If its redshift instead shows it receding at 7,300, then 300 kilometers per second of real motion is pushing it away from us beyond the expansion. If the redshift shows 6,700, then 300 kilometers per second of real motion is pulling it toward us, against the expansion. That leftover, that small difference, is a single thread in the cosmic flow we have been mapping. The difficulty hiding inside this is the reason the whole field is so demanding. At large distances, the expansion velocity is huge, many thousands of kilometers per second, while the peculiar velocity we are hunting is usually only a few hundred. We are trying to find a small number by taking the difference between two much larger numbers. And whenever you subtract two big numbers to find a small one, any error in the big numbers lands directly on the small result, magnified. A distance that is off by even a few percent throws the predicted expansion off by hundreds of kilometers per second, which can swamp the very peculiar velocity we were trying to measure. This is why distances have to be extraordinarily good, and why a small error in distance is the single largest source of doubt in every flow map ever made. The grand picture of pulls and pushes lives or dies on how well we can measure how far away each galaxy truly is. There is one more honesty I owe you here, because even the expansion rate is not perfectly settled. Different ways of measuring how fast the universe expands give slightly different answers, somewhere between about 67 and about 73 kilometers per second per megaparsec, and that disagreement is one of the live, unresolved tensions in cosmology right now. It does not break the method we just walked through, but it is a reminder that even the number we subtract carries its own uncertainty, and careful astronomers carry that uncertainty all the way through to the end rather than pretending it away. What stays with me about all of this is how humble the foundation is beneath something so vast. Every sweeping map of cosmic flows, every claim about Shapley and the Great Attractor and the Dipole Repeller, every river of 100,000 galaxies rests on this one quiet act repeated thousands of times. Measure a redshift, measure a distance, subtract the expansion, keep what remains. The majesty of the largest structure we belong to is built, in the end, on careful arithmetic and honest error bars, done patiently for galaxy after galaxy. But all of it depends on that one independent distance, the distance we are forbidden to take from the redshift, because the redshift is contaminated by the very motion we are trying to find. We need to know how far away a galaxy is by some completely separate means, something that never touches its redshift at all. And that raises the question the entire enterprise has been quietly standing on from the beginning. How do you measure an honest distance to a galaxy tens or hundreds of millions of light years away, a place no instrument will ever reach, using nothing but the light it sends us? Every method for measuring distance across the universe rests on one fact about light. Light spreads out as it travels, and as it spreads, it dims in a precise and predictable way. A source twice as far away appears 1/4 as bright, 3 times as far, 1/9 as bright, 10 times as far, 1/100th. The dimming follows the square of the distance, exactly and always. This means that if you ever know how bright something truly is, how much light it actually pours out, you can compare that to how bright it merely appears from here, and the gap between the two tells you exactly how far away it must be. The whole problem of cosmic distance comes down to a single missing piece. We can always measure how bright a galaxy appears. What we almost never know is how bright it truly is. For galaxies, that missing piece looks hopeless at first. Galaxies are not all the same. Some are giant and blazing, others small and dim, and they span an enormous range of true brightness. Two galaxies that appear equally bright in our sky could be a modest galaxy nearby or a giant one far away, and from their appearance alone there is no way to tell which. Without some independent way to know a galaxy's real luminosity, the inverse square law gives us nothing, because we have no true brightness to compare the apparent brightness against. For a long time, this was the wall. We had the perfect tool for turning true brightness into distance, and no reliable way to learn the true brightness of a galaxy in the first place. The way through that wall was found in the year 1977 by two astronomers named Brent Tully and Richard Fisher. They were studying spiral galaxies, the flat rotating disks like our own Milky Way, and they noticed a relationship that no one had pinned down so cleanly before. The speed at which a spiral galaxy rotates is tightly connected to how much light it truly gives off. Fast spinning spirals are intrinsically luminous. Slow spinning spirals are intrinsically faint. The connection is steady and predictable enough that if you can measure how fast a galaxy spins, you can estimate how bright it truly is. And that was the missing piece. A property that reveals a galaxy's real luminosity, finally giving the inverse square law something to work with. The reason the relationship exists reaches straight down into what a galaxy is. A spiral galaxy holds itself together by gravity, and the speed its disk rotates is set by how much total mass that gravity has to work with. A heavier galaxy needs to spin faster to hold its outer regions in orbit, so rotation speed is really a measure of total mass. And a galaxy with more total mass generally contains more stars, which means it produces more light. So the chain runs from rotation speed to total mass to number of stars to true brightness, each link grounded in real physics. Measure how fast a spiral turns, and you are indirectly measuring how much of it there is, and therefore how much light it must be sending into the universe. What makes this genuinely useful is that we can measure a galaxy's rotation speed without knowing its distance at all. As a spiral galaxy spins, one side of its disk is turning toward us, and the other side is turning away. The side coming toward us has its light shifted slightly bluer, and the side moving away has its light shifted slightly redder. We met that same hydrogen signal earlier, the radio emission at a wavelength of about 21 centimeters. In a spinning galaxy, that single sharp signal gets spread into a wider band because part of the galaxy is approaching and part is receding, and the faster the galaxy spins, the wider that spread becomes. So we measure the width of that radio signal, and the width tells us the rotation speed directly. It depends only on how the galaxy is moving within itself, not on how far away it is or how bright it appears, which is exactly what we needed. Now every piece finally connects. Measure the width of a spiral galaxy's hydrogen signal, and you have its rotation speed. Feed that rotation speed into the Tully-Fisher relationship, and you have its true brightness. Compare that true brightness to how bright the galaxy actually appears in our telescopes, and the inverse square dimming hands you the distance. At no point in that chain did we ever use the galaxy's redshift. The distance came entirely from the galaxy's rotation and its appearance, completely independent of the motion we were trying to measure. And that independence is everything, because now we can carry this clean distance back to the subtraction from before, predict how much of the redshift is just expansion, subtract it, and at last reveal the galaxy's true peculiar velocity, its real fall through space. I find it remarkable how long this quiet relationship waited to show what it was worth. When Tully and Fisher published it in 1977, it was a useful tool for estimating galaxy distances, valuable but not world-changing. It took decades of patient work, better instruments, and far larger surveys before that single relationship could be applied to thousands upon thousands of galaxies at once. When it finally was, it became the backbone of the great surveys that measured the cosmic flows and revealed the structure we now call our home. A modest rule about how fast galaxies spin, sitting in a paper for more than 30 years, turned out to be one of the keys that redrew our address in the universe. Some discoveries do their most important work long after the people who made them have moved on. The Tully-Fisher relationship has scatter in it, meaning galaxies do not follow it perfectly, so every distance it gives carries a margin of uncertainty. It applies to spiral galaxies, the rotating disks, but not to the great elliptical galaxies, which do not spin as orderly disks and need an entirely different relationship to estimate their brightness. Each galaxy type demands its own carefully calibrated method, and each method carries its own errors. This is the same uncertainty we faced before, the few percent doubt in distance that becomes a large doubt in peculiar velocity, and it never fully goes away. Every distance in every flow map is a best estimate with an honest error attached, not a perfect number. Even so, the achievement is staggering when you step back from it. Using nothing but the light and radio signals that galaxies send us across tens and hundreds of millions of light years, we can now measure how far away they are, separate their true motion from the expansion of space, and lay each one down as a point with a known distance and a known velocity. We have done this for thousands of galaxies, building a vast catalog of positions and motions across our region of the universe. But a catalog of thousands of separate points is still only a list. A list of distances and velocities is not yet a map, and it is certainly not yet a flowing structure with rivers and a focus and a boundary. Something has to turn those scattered, individual measurements into a single coherent picture of how everything moves together. So the next question is not how we measure one galaxy, but how we assemble thousands of them into one. Who took this scattered field of individual points, each with its own uncertainty, and reconstructed from it the smooth, continuous flow of an entire supercluster? And how could anyone trust a map built from measurements that each carry their own margin of doubt? By the early 2010s, we had done the hard work of the last several parts not once, but thousands of times over. For roughly 8,000 galaxies, we had measured a distance and a redshift, separated the expansion from the real motion, and arrived at a peculiar velocity, a single arrow showing which way that galaxy was truly falling and how fast. 8,000 galaxies, each with its own measured motion, scattered across our region of the universe. It was an extraordinary amount of work, and it still was not a map. It was 8,000 separate facts, each true on its own, with vast stretches of empty space between them where we had measured nothing at all. The reason that scatter of points cannot simply be connected into a flow comes down to two stubborn problems. The first is that galaxies only exist where they exist. We can measure a motion only where there is a galaxy to measure, and galaxies leave enormous gaps between them, regions millions of light years across where we have no data point of any kind. The second problem is that every single measurement carries error. Each peculiar velocity we found is a small number pulled from the difference between two large ones, and so each arrow has a margin of doubt attached, sometimes a large one. So we are asked to build a smooth, continuous picture of how everything moves, out of measurements that are scattered, full of holes, and individually uncertain. Connecting the dots directly would be building a confident map out of unconfident points, and it would be wrong almost everywhere. What rescues the situation is that the motion of galaxies is not random or arbitrary. Every peculiar velocity is caused by gravity, and gravity comes from the distribution of mass throughout space. Mass in the universe is not scattered at random either. It clumps into a structured pattern of dense filaments and empty voids, and that pattern follows statistical rules we understand well from both observation and theory. This means that before we ever look at the data, we already know something about what a realistic velocity field is allowed to look like. Real flows are smooth on large scales. They do not jump wildly from one point to the next. They follow from a mass distribution that obeys known patterns. That prior knowledge is the missing ingredient that lets us fill the gaps responsibly instead of guessing blindly. The tool that combines these two things is a statistical method called the Wiener filter. What it does, in plain terms, is take all the noisy, scattered measurements we have and find the single most probable smooth flow that is consistent with both the data and everything we know about how the universe is structured. Where our measurements are dense and agree with each other, the reconstructed flow follows them closely because the data is trustworthy there. Where our measurements are sparse or uncertain, the method does something quietly honest. It relaxes back toward the calm cosmic average, the state of no unusual motion, because in the absence of good data, the most probable answer is simply the typical behavior of the universe. It does not invent dramatic flows in places it cannot see. It fills the unknown regions with the most likely values and grows more cautious the less it knows. The reconstruction does not only produce a best estimate flow. At every location, it also reports how confident it is, how much that arrow can be trusted, how much the data constrained it versus how much it had to fall back on assumption. A map that tells you where it is sure and where it is guessing is a fundamentally different thing from a map that hides its own ignorance. We trust the picture of our cosmic flows not because it claims perfect knowledge, but precisely because it is built to admit, at every point, exactly how much it does not know. Its honesty is the source of its authority. The raw material for all of this came from a long collaborative effort called Cosmic Flows, a project to measure the distances and motions of galaxy after galaxy and assemble them into one enormous catalog. The first maps of our supercluster drew on around 8,000 galaxies, and in the years since, that catalog has grown to tens of thousands, each edition sharpening the picture. Behind that catalog were people who spent large portions of their working lives on it. Hélène Courtois helped lead the Cosmic Flows surveys and worked to carry the result out to the wider world so that people could actually see it. Daniel Pomeretti built the visualizations that turned columns of numbers into a three-dimensional flow anyone could look at and finally comprehend. Yehuda Hoffman developed much of the reconstruction work that filled the gaps and drew out the hidden patterns, including the great repelling void we met earlier. Brent Tully, whose rotation relationship made the distances possible in the first place, was part of the same effort decades later. This was not a single flash of insight by one mind. It was years of patient, careful, international work, measurement piled on measurement, until a structure no human had ever seen came slowly into view. The largest structure any of us belongs to was not handed to us by a single telescope on a single night. It was assembled by hand, galaxy by galaxy, across the careers of people working in different countries, each contributing a piece, none of them able to see the whole until the pieces were finally brought together. And the result they built does not pretend to a certainty it has not earned. It is a careful, honest reconstruction that shows us our place while openly marking the limits of its own vision. There is something deeply human in that, a map of the heavens that is brave enough to say where it cannot see. When that reconstructed flow was finally complete, it let us do something we had never been able to do before. With a velocity known at every point, not just where galaxies happen to sit. We could trace the paths that matter follows through our region, the continuous lines of the flow. We could follow those lines outward and watch where they led. And when we did, the galaxies of our entire neighborhood, the streams we once called separate superclusters, all traced their flow lines toward the same focus, converging into one structure. But the same reconstruction revealed something stranger at the edges, a place where the flow lines stopped converging toward our focus and bent instead toward a different one, somewhere else entirely. That dividing surface was the boundary of our supercluster, and it was a kind of boundary astronomy had never drawn before. What kind of border has no wall, no edge of matter, nothing physical sitting along it at all, and still decides which of two great structures a galaxy belongs to, based on nothing but the direction it is falling? With the flow reconstructed at every point in space, we can finally ask the simplest possible question of any galaxy and get an answer. If this galaxy keeps following the motion it has right now, where does it end up? We take its position, we read the direction the flow is carrying it, and we follow that path forward, step by step, letting each new position tell us the next direction. The line we trace is the galaxy's flow line, the route it is destined to follow if nothing changes. And when we follow it far enough, it arrives somewhere. It converges on a focus, a point where the surrounding flow all comes together. Every galaxy in our region has such a line, and every line leads to some destination. Trace those lines for every galaxy across a wide stretch of the universe, and something orderly appears. The galaxies sort themselves into groups, not by where they sit, but by where they are going. All the galaxies whose flow lines lead to our focus, the great mass concentration toward Norma and Shapley, form one set. All the galaxies whose flow lines lead to some other focus, in some other direction, form a different set. The set of everything that shares our destination, everything falling the same way we are, toward the same point, is what we named Laniakea. It is not defined by a wall around it or by where the galaxies happen to be dense. It is defined entirely by a shared destination. The boundary of that structure is the surface where the destination flips. Stand at a point just inside Laniakea, and the flow there carries you toward our focus. Move a little farther out, across a certain invisible surface, and the flow at that new point carries you toward a completely different focus instead. That surface, the place where one step in one direction sends you toward our center and one step the other way sends you toward someone else's, is the edge of our supercluster. Nothing physical sits along it. There is no wall there, no thinning of matter, no marker of any kind you could detect by looking. The boundary exists only in the motion, only in the fact that on one side everything falls toward us and on the other side everything falls away. This way of defining a structure has a name borrowed from the mathematics of how things flow. It is called a basin of attraction, which means the full collection of every location whose motion eventually converges to the same focus. Laniakea is the basin of attraction for our focus, the complete set of all the places whose flow lines end at our center. The boundary between our supercluster and the next is simply the dividing surface between two neighboring basins, the line past which the flow stops belonging to us and starts belonging to them. It is a definition built entirely from direction and destination, and it contains no reference to matter sitting at the border at all. Every cosmic structure we ever named was defined by where matter gathers. A galaxy is where stars are dense. A cluster is where galaxies are dense. A supercluster, in the old way of thinking, was where clusters were dense. Density was the whole idea. You found a structure by finding a crowd. The basin of attraction throws that out and replaces it with something completely different. A structure is no longer where matter is. It is where matter is going. Identity by destination, not by contents. The consequence of that switch is genuinely disorienting when you sit with it. Two galaxies could be in regions of identical density, surrounded by the same number of neighbors, looking exactly alike in every way that the old definition cared about. And they could still belong to two entirely different superclusters, simply because one is falling toward our focus and the other is falling toward a different one. What separates them is not where they are or what surrounds them. It is the direction of their fall. Your membership in the largest structure you belong to is not a matter of your address. It is a matter of your trajectory, the way you happen to be moving through space right now. We even know who our neighbors are across that invisible line. On the far side of one long stretch of Laniakea's boundary lies another supercluster, called Perseus Pisces, with its own focus and its own basin. The galaxies just on their side of the line are falling away from us, toward their own center, while the galaxies just on our side are falling toward ours. Between the two, there is no wall, no gap, no physical edge. There is only the surface where the flow parts, where our basin ends and theirs begins. Two great structures pressed against each other along a border made of nothing but opposing directions of motion. A boundary built from motion has a property that a wall never could, and it is the quiet seed of everything still to come. A wall stays where it is. A boundary made of motion can move, because motion itself can change. The focus our flow lines lead to today is set by the way mass is arranged in this era of the universe, and as the cosmos evolves, that arrangement shifts. The edge of our home is not carved into space permanently. It is a description of how things are moving in our present moment, and a description of motion is only ever true for now. We will come back to what that means, because it changes what Laniakea fundamentally is. We are used to home meaning a place with edges, something you could walk to the border of and stand on. The largest home we have is nothing like that. Its border is invisible, made of motion rather than matter, and you belong to it not because of where you are, but because of which way you are falling. There is no ground beneath this structure, no wall around it, no center you could ever stand at. There is only a shared direction, a vast company of galaxies all leaning the same way, and the quiet agreement of that shared fall is the only thing that makes us one place at all. If our entire structure is defined by motion, then that motion ought to be fully explainable. Every pull from every mass, the Great Attractor, Shapley, every cluster, and every push from every void, including the Great Repeller behind us, should add together into one total. And that total should come out to exactly the 600 kilometers per second we measure ourselves moving. When astronomers actually carry out that sum, adding every known pull and push to see if it matches our real motion, the answer comes remarkably close. It almost adds up. But not quite. And the small piece that does not fit is a story of its own. We now have everything we need to run the most honest test in this entire story. On one side, we have a motion we have measured directly. Our region moving a little over 600 kilometers per second in a specific, known direction, read from the warm and cool patches of that ancient light. On the other side, we have a catalog of every major mass that pulls on us, and every great void that pushes, the Great Attractor, the Shapley Concentration, the Dipole Repeller, the nearer clusters, all of it. The test is simple to state. Add up every one of those pulls and pushes and see whether they combine to produce exactly the motion we actually feel nothing of. If our understanding is right, the sum should match the measurement. Adding up gravity means respecting that every pull has a direction. Each mass tugs us toward itself, with a strength set by how much mass it holds and how far away it sits, weaker the farther it is. Each void, as we saw, effectively pushes us away from itself because of the matter it fails to balance on the far side. Every one of these is an arrow, pointing a certain way with a certain strength. To find the total, you lay all those arrows together, accounting for the direction of each, and see what single combined arrow they produce. That combined arrow is the motion our model predicts. And then you set it next to the motion we truly measure. And you ask whether they point the same way and carry the same speed. When astronomers carry out that sum, the answer is close enough to be a real triumph. The predicted direction lands near the measured direction. The predicted speed lands near the measured speed. The motion of our entire region, all 100,000 galaxies of us, is largely explained by adding up the gravity of the matter we can actually map. It is easy to let that pass by, so I want to stop on how remarkable it is. We took the visible structure of the nearby universe, weighed it, accounted for its pulls and its absences, and reproduced the real motion of our galaxy through space. The fact that it works at all means we are not confused about the basic nature of what moves us. Gravity, acting across hundreds of millions of light years, explains where we are going. But the way that total breaks down is humbling, and it changes how you should picture our place. Only a modest share of our motion comes from within Laniakea itself, from the matter inside the structure we call home. A large fraction comes from the Great Attractor region, which does not sit at the heart of our supercluster, but out near its edge, in the direction of its boundary. And a substantial part comes from Shapley, which lies beyond our boundary entirely, outside Laniakea, in another basin altogether. So the thing mostly moving us is not the interior of our own home. It is the rim of our home and the things that lie outside it. Sit with what that means about where we stand. We are not being carried along by the deep center of our own supercluster. We are out near its edge, leaning outward, pulled more strongly by what lies beyond our borders than by what lies within them. The structure we belong to is real, and we are inside it, but our motion is mostly a response to things at its boundary and past it. We live on the outskirts of Laniakea, pulled hardest by what lies toward its boundary and beyond, not by the distant center we nominally belong to. Our home shapes us less than its surroundings do. The match between prediction and measurement is close, but it is not perfect, and the leftover matters. When you add every pull and push we can identify, the total comes near our true motion but does not land exactly on it. A small residual remains, a piece of our motion that the known sources do not quite account for. There are two honest explanations for that gap, and we cannot yet rule out either one. The first is that there is mass we have not mapped, hidden behind the plane of our galaxy in the zone of avoidance, or simply too far out to have been surveyed yet, and that unmeasured mass is contributing a pull we have not counted. The second is stranger. It is the possibility that our motion extends to scales larger than our maps reach, that we are part of a flow broader than anything we have been able to measure, drawn by something beyond the edge of our surveyed volume. This is where a deeper idea enters, the idea of convergence. In principle, as you survey a larger and larger volume around us, the pulls from distant matter should increasingly cancel one another out, because on the largest scales the universe is nearly the same in every direction. Pull from one far side gets balanced by pull from the other far side, and the net contribution from great distances should fade toward nothing. If that holds, then beyond some radius our motion should be fully explained, and adding more distant volume should change nothing. Whether our motion actually settles down like that, within the volume we expect, or whether some broad flow stubbornly persists to larger scales than it should, is one of the real open questions in this field. We will come back to it, because the answer touches the foundations of our entire model of the universe. What stays with me about this whole accounting is how much trust it places in addition. We can weigh the invisible mass of the cosmos, the concentrations we cannot see directly, and the voids that contain almost nothing, by doing nothing more than checking whether our own quiet motion adds up. If the sum matches, we understand our place. If it does not, we are missing something, and the size of the mismatch tells us how much. And the remarkable thing is that, for the most part, it does add up. Our 600 kilometers per second, the motion no nerve in your body will ever report, is very nearly fully explained by the gravity of everything around us. We do understand, in broad strokes, why we are moving the way we are. But notice the assumption buried under every step we just took. The entire exercise treated Laniakea as one thing, a structure with a mass and an edge that we could weigh, sum, and place on a balance against our motion. We spoke of it as an object, a home, a member of the cosmic catalog, something with enough solidity to be measured. And yet everything we learned about its boundary should make us pause. A structure held together by no force, with no wall and no surface, defined only by a direction of falling that we already know will not last, may not be an object in any real sense at all. We have weighed Laniakea, mapped it, and drawn its borders. But is it truly a thing that exists, or is it something else entirely? A pattern we have mistaken for an object, real enough to measure, and yet not real in the way a galaxy or a cluster is real. Everything now depends on a single word that we have been using loosely, and it is time to define it exactly. That word is bound. A structure is gravitationally bound when its own gravity is strong enough to hold its parts together against the expansion of the universe. In a bound structure, the parts circle a common center, held in by their mutual pull, and they stay together permanently. Space may be expanding everywhere else, but inside a bound structure that expansion does not win. Gravity has already closed the deal. The parts are committed to each other, and they will remain together for as long as the structure exists. Our galaxy is bound. The hundreds of billions of stars in the Milky Way orbit its center, held together by their combined gravity, and the expansion of the universe will never pull them apart. A galaxy cluster is bound too. Its hundreds or thousands of galaxies orbit the cluster's center of mass, locked together, and they will stay locked together while the universe expands around them. These are real, lasting objects in the fullest sense. The expansion of space happens in the gaps between them, in the open distances, but never inside them. Once something is bound, it has stepped out of the expansion's reach. It is a permanent resident of the universe. So, the decisive question for Laniakea is whether it is bound. Is the combined gravity of the whole supercluster strong enough to hold its 100,000 galaxies together against the expansion, so that they will one day finish falling and assemble at the focus we mapped? We have measured the flow. We have seen the galaxies leaning toward their common center. It would be reasonable to assume that flow is the beginning of a gathering, the early stage of a structure pulling itself together. But when astronomers measured whether the gravity is actually strong enough to win, the answer came back clearly. It is not. Laniakea is not gravitationally bound. The reason is that the expansion of space is working against the flow, and over the largest distances, the expansion is stronger. The galaxies in the outer parts of Laniakea are indeed leaning toward the focus right now, and that motion is real. But the space between those outer regions and the center is stretching, carrying them outward, and it is stretching faster than their weak shared gravity can reel them in. The flow we measure is a true description of which way things are leaning at this moment. It is not the description of a gathering that will succeed. The outer galaxies of Laniakea will never reach the center they appear to be falling toward. They will be carried away by the expanding space between, long before they arrive. The convergence we mapped, the flow lines all pointing toward one focus, is not the early stage of a structure assembling itself. It is a tendency that exists now and will never be fulfilled. Laniakea is caught in the act of trying to come together and losing because the expansion of the universe is pulling its parts apart faster than gravity can collect them. Everything we measured is accurate. The galaxies really are leaning that way. The focus really is pulling. And none of it will finish. The gathering we are watching is one that cannot complete. That forces a distinction we cannot avoid, and it cuts to what we even mean by a thing. A bound object will persist and complete. Its parts are committed. Its future is settled. It is solid in the deepest sense the universe allows. An unbound structure is different in kind, not just in degree. It is a configuration that is true at this moment and will come apart, a description of how matter happens to be moving right now, with no guarantee of a future. The line between bound and unbound is not a small technicality. It is the line between a lasting object and a passing pattern, between something that exists and something that is merely, for now, the case. Which side of that line does Laniakea fall on? It is rigorously real as a description of how everything is moving in our era. The boundary we drew is correct. The focus is correct. The basin of attraction is a precise, measurable, non-arbitrary fact about the present motion of 100,000 galaxies. But it is not an object in the way a galaxy is, or a cluster is. It is a pattern in the motion of matter at this cosmic moment, accurate today and dissolving toward tomorrow. We did not discover a permanent structure. We discovered a true description of a temporary state. The largest thing any of us belongs to, the home we just spent all this time learning to map, weighing and bounding and tracing, is not a permanent place at all. It is a configuration that happens to be true while we are here to measure it. Our deepest sense of cosmic belonging, the feeling that we are part of something vast and structured, turns out to be belonging to a pattern that is already, slowly, coming undone. It brings a kind of vertigo, gentler than fear but stranger, the feeling of learning that your largest home was never built to last. But I do not want to leave you there, because that conclusion is incomplete, and the incompleteness matters. A pattern that is real right now is still real right now. The flow is happening. We are inside it. 100,000 galaxies truly are leaning the same way, and we truly are among them, and that is the largest true thing about our motion through the universe. Impermanence is not the same as unreality. The fact that Laniakea will not last does not make it false today, any more than a single day is false because it ends. We belong to something vast and real and passing, all at once, and learning that it is passing does not erase that we belong. Still, knowing the structure is unbound leaves an obvious and pressing question, the one that takes us into the next part. If Laniakea is being pulled apart by the expansion of space faster than it can assemble, then exactly how does that undoing happen? Why does the structure come apart from its outer edges first, and why does the long fall toward the center never reach its end? We have learned that our home will not hold together. Now we have to watch, in detail, exactly how it comes undone, and why the gathering we are part of was always going to fail. The expansion of the universe is not coasting along at a steady rate, slowly losing speed the way you might expect. It is accelerating, growing faster over time, and the cause is what we call dark energy. Dark energy appears to be a property of empty space itself. Every region of space seems to carry a small amount of this energy, and it acts to push space to expand. As space expands, there is more space, and more space means more of this energy, which pushes the expansion to go faster still. The expansion feeds on its own results. Rather than slowing down as gravity tries to rein it in, it speeds up, and over the long run, nothing we know of stops it. At every distance in the universe, two opposing influences are at work on any pair of regions. Gravity pulls them together. The expansion, driven by dark energy, carries them apart. Which of the two wins is not fixed. It depends entirely on how far apart the two regions are. And the reason distance is the deciding factor reveals why a structure the size of Laniakea was doomed from the start. Gravity weakens with distance, growing fainter the farther apart two regions sit, and it depends on how much mass is doing the pulling. The expansion works the opposite way. The more space there is between two regions, the more space there is to stretch, so the farther apart they are, the faster the expansion drives them apart. Put those two trends together, and a clear dividing distance appears for any given mass. Within that distance, gravity is strong enough to win, and the regions stay bound. Beyond that distance, the expansion wins, and the regions are carried away from each other no matter how much they lean together. Now place Laniakea against that dividing distance. Our supercluster spans roughly 500 million light-years, and that is far larger than the distance within which its total mass could hold things together. The concentrated mass near the center can keep its close inner regions bound. But the outer reaches of Laniakea sit well beyond the distance where gravity can win. Most of the volume of our supercluster is already in the regime where the expansion is stronger than the pull. The structure is too big for its own gravity. It was never massive enough to hold a region that wide together against an accelerating expansion. The outer edges are where this loss begins, and two effects conspire to make it so. The galaxies at the edge of Laniakea are the farthest from the central mass, which means gravity reaches them most weakly. They are also separated from the center by the widest span of space, which means the expansion carries them away most strongly. Weakest pull and strongest push, both landing on the same galaxies at the same time. So the edges are the first to be lost. The outermost galaxies, the ones leaning toward our focus right now, will detach from the flow, carried off by the expanding space between them and the center they were falling toward. From there, the undoing works its way inward. Once the outermost layer has been carried away, the new outermost layer is now the farthest and the most weakly held, and it goes next. Layer by layer, the structure comes apart from the rim toward the center, each region in turn crossing the distance where expansion takes over. The inward lean we measure today is real, but for the outer parts, it is a lean that will never arrive. Once you account for the expanding space they must cross, their true future is not arrival at the center, but departure from the structure entirely. They are falling inward and being carried outward at once, and the outward carrying wins. This is why the gathering never completes. The convergence we mapped, all those flow lines pointing to one focus, is a present tendency, not a future event. For most of Laniakea's volume, the expansion already dominates, so the great fall toward the center is one that the outer regions can never finish. What survives is only the inner, densest cores, the places where mass is concentrated tightly enough to stay bound. The Virgo cluster and the other dense clusters within our region will hold together. The wider structure that links them, the flowing supercluster we call Laniakea, will not. And the situation only worsens with time because of a deep imbalance between matter and dark energy. As the universe expands, matter spreads out and thins, so its gravity grows weaker everywhere. Dark energy does not thin out because it is a property of space itself, and there is only ever more space. So as the eons pass, dark energy grows steadily more dominant over matter, and the dividing distance where gravity can still win shrinks. Regions that are bound today will cross into the losing side tomorrow. The bound cores that survive will themselves grow more isolated and, over immense spans of time, smaller, as the reach of gravity contracts and the expansion claims more and more. All of this plays out over tens of billions of years, far longer than the present age of the universe, and we do not watch it happen. We project it by taking our best current understanding of dark energy and running the clock forward. And the nature of dark energy is one of the deepest unknowns in all of physics. We can measure its effects, but we do not understand what it is, and if it behaves differently over time than we assume, the distant details of this future could change. What is not in serious doubt is the basic outcome. A structure as wide as Laniakea, with as little binding gravity as it has, does not hold together against an accelerating expansion. So our home does not end in any violence. There is no collision, no explosion, no moment of destruction. Laniakea simply, quietly, stops being a single coherent pattern as the expanding space within it outgrows the reach of its own gravity. The flow fades, the boundary dissolves, the dense cores remain, scattered and bound, each holding itself together while the connections between them stretch away into nothing. The structure does not die. It disperses, gently, over a span of time, so long it strains the meaning of the word. But that dispersal raises a question stranger and lonelier than the dispersal itself. If the connecting structure dissolves, and everything beyond each bound core is carried out of view by the expanding space, then what will be left for anyone living in that far future to see? What does the universe look like to an observer born after the flow has faded, when the sky has emptied of everything except their own bound region? And the most unsettling part of that question is not what they will see. It is what they will no longer have any way to know. Picture an astronomer born 100 billion years from now, inside the bound region that was once our local group, long after it has merged into a single galaxy. She points her telescope at the sky and begins to do exactly what we do, carefully, honestly, with good instruments and a sharp mind. And she sees one galaxy, her own, surrounded in every direction by black, empty space. No other galaxies, no structure, no flow. Nothing beyond the edge of her own galaxy, but darkness that goes on without end. The sky is empty for her because of everything we learned in the last part. The accelerating expansion has carried every galaxy outside her bound region away, and as they receded, their light was stretched to longer and longer wavelengths, growing dimmer and redder until it faded below anything any instrument could detect. But it is worse than fading. Those galaxies have crossed what we call the cosmic horizon, the distance beyond which space is receding faster than light can travel back toward us. Once a galaxy crosses that horizon, its light can never reach the observer again, no matter how long they wait. The galaxies do not merely become too faint to see. They leave contact entirely, sealed away on the far side of a boundary that light itself cannot cross. Even the oldest light goes dark. The faint relic glow we used as our own speedometer, the light left over from the universe's hot beginning, is being stretched by the same expansion. Its wavelength grows longer with time, and over a long enough span it stretches until it, too, falls below any possible detection. The single clearest piece of evidence that the universe was once hot and dense and beginning, the fingerprint of the entire origin, fades out of reach. The future astronomer cannot detect it, because by her era it will no longer be detectable by anything. The evidence will not be hidden, it will be gone. Consider what that does to what she can know. We understand that the universe expands because we can see distant galaxies moving away from us, their redshift growing with distance, a pattern visible across thousands of galaxies. She has no external galaxies to measure. With nothing beyond her own to compare against, there is no recession to detect, no expansion to discover, no way to even suspect that space is growing. We know the universe had a beginning because we can still measure the relic glow. She cannot measure it, so she has no reason to think there was a beginning at all. Every line of evidence we use to reconstruct the history of the cosmos will, by her time, have left the observable universe. So she reaches a conclusion that is careful, rigorous, and completely wrong. One galaxy, alone, unchanging, eternal, sitting in an infinite and empty void. No expansion, no beginning, no other galaxies, no clusters, no superclusters, no flow, no Laniakea. And she would not be making a mistake. Every observation available to her would be consistent with that static, lonely picture. She would have done good science, honest science, and arrived at a false history of the universe, not through any error of reasoning, but because the evidence required to know the truth would no longer exist anywhere she could reach. Truth in science depends on evidence remaining available to be found. The facts of the deep past do not change. There really was an expansion. There really was a hot beginning. There really were 100,000 galaxies leaning together in the structure we call home. But in that far future, all of it becomes unknowable, not because it did not happen, but because every trace of it will have been carried beyond the reach of any instrument that could ever be built. The universe will still have a history. There will simply be no way left to read it. Cosmologists have pointed out that this puts us in a strangely privileged moment. We live in an era when the universe's history is still visible, when the distant galaxies have not yet receded out of view, when the relic glow can still be measured, when the expansion can still be detected. The evidence is more accessible now than it will ever be again, and from here it only diminishes. The astronomers of the far future will not be less capable than we are. They will simply be cut off from the data, born into a universe that has quietly erased the record of its own origins. We happen to be living while that record is still open. That gives a quiet weight to what we are doing right now, in this very work of looking and measuring and mapping. We are among the observers who get to see the universe while it still shows its past, who can still trace the cosmic flows, still weigh Laniakea, still detect the glow of the beginning. There may be minds in the far future who can never recover any of this, who will look out at an empty sky and never know what it once contained. To observe carefully now, and to record what we find, is a form of stewardship across time. We are keeping the knowledge of where everything came from, for as long as anyone is able to keep it. The map of our home is not only a map for us. It is a record made during the narrow span of time when the record can still be made at all. Every careful measurement of the flow, every galaxy added to the catalog, is part of holding open a memory of the universe, that the universe itself is slowly closing. We are not only learning where we are witnessing, on behalf of everyone who comes after, a cosmos that will not always be willing to show itself. Even now, even while the evidence is at its most open, there is a part of the present universe we cannot observe at all. A full fifth of the sky is sealed shut, not by the expansion of space or the passage of deep time, but by the body of our own galaxy standing in the way. And we still do not fully know what is hidden behind it. Before we worry about what the future will be unable to see, we have to ask honestly how much of the universe we ourselves are still missing, right now. We have already met the band of sky that the Milky Way blocks, the zone of avoidance, and the methods we use to see partway through it. Near-infrared light, the radio signal of hydrogen at 21 centimeters, the X-ray glow of hot cluster gas, all of them recover galaxies the dust had hidden. But those methods have limits, and the limits are worst exactly where it matters most. Right along the central line of our galaxy's plane, where the stars and dust are thickest, the obscuration becomes so complete that even infrared and radio surveys grow patchy and uncertain. We have pushed our vision inward from both edges of the band. The narrow strip down the very middle remains the single hardest patch of sky in all of observational astronomy, and parts of it are still nearly blank. The size of that gap is not small. Roughly a fifth of the entire sky beyond our galaxy falls within the band, and while we can now see into much of it, the worst few degrees along the midline still resist every instrument we own. We have not closed the blind spot, we have only narrowed it. And the part that remains is not empty sky we can safely ignore. It is a strip that runs all the way around us, cutting across every direction we might look, including some of the directions our own motion points toward. This is where the gap stops being a historical inconvenience and becomes a live problem. Remember the small residual from before, the piece of our motion that the known pulls and pushes did not quite account for. One honest explanation for that leftover is mass we have never counted because it sits hidden behind the densest part of the band. The zone of avoidance is not a solved puzzle from the past. It is an open source of uncertainty in our present map of what moves us, right now, today. Some unknown fraction of the gravity steering our region could be coming from concentrations of matter we simply cannot see. That this is a real possibility, and not just a cautious hypothetical, was proven only recently. In the year 2017, a survey of thousands of galaxies around the edges of the band revealed an enormous, previously unknown concentration of galaxies, sitting partly behind the plane, several 100 million light-years away, in the direction of the constellation Vela. It is now called the Vela Supercluster, and it appears to be a major structure, comparable in scale to the great superclusters we already knew. The astronomers who found it, working again from the difficult edges of the zone of avoidance, had uncovered a giant that had been hiding in plain sight for the entire history of astronomy. And its densest core lies right in the blind strip, so even now we cannot fully measure its size or its mass. We know it is there. We do not yet know exactly how large it is. Sit with what that discovery means. An entire supercluster, a structure spanning hundreds of millions of light-years, stayed completely hidden until a few years ago, and we still cannot see its heart. If something that large can hide behind our galaxy undetected into the 21st century, then the honest position is unavoidable. We cannot rule out that other concentrations are hidden there too, including ones massive enough to be contributing to our motion. The thing we cannot see is not guaranteed to be small or unimportant. We just found proof that it can be neither. The way we estimate what hides behind the band rests on an assumption we should name out loud. When we fill in the blind strip, we assume the universe behind it is statistically similar to the universe everywhere else, the same average density, the same kinds of structures. That assumption is reasonable, and most of the time it is probably close to true. But it is an assumption, not an observation. A real surprise directly behind the plane, an unusual concentration that does not match the average, is exactly the kind of thing this method would miss, because the method works by assuming there are no surprises. Vela was a reminder that the assumption can be wrong. We account for some of the mass that moves us by assuming it resembles what we can see, rather than by actually seeing it. The residual motion we could not explain might be exactly this, the pull of matter hidden in the band that our assumption smoothed over. Or it might be something else entirely, something the hidden mass cannot account for no matter how we estimate it. We cannot yet tell the two apart, and refusing to pretend otherwise is not a weakness of the science. It is the science being honest about the edge of its own vision. What stays with me is the particular humility this forces on us. We are trying to map the largest structures in existence, and we have to do it with a permanent blind spot built into our view, placed there not by any failure of ours, but by the simple accident of living inside a galaxy whose own body blocks a fifth of the sky. We did not choose that vantage point. We work around it as best we can, recovering what we can in borrowed wavelengths, and we mark the gap clearly on the map rather than quietly filling it in and hoping. A map that admits where it cannot see is worth more than one that pretends to see everything. The blind spot will shrink in the years ahead. New radio surveys and larger telescopes will detect more and more hidden galaxies by the faint hydrogen signal that crosses the dust, pushing our vision deeper into the band than ever before. Much of what is hidden today will be recovered. But the narrowest, densest sliver right along the midline may never fully open to us, not while we remain inside this galaxy, looking out through its thickest part. Some portion of the universe directly behind us may stay hidden for as long as our species exists. And here the uncertainty changes character, from missing mass to something deeper and stranger. Because even if we set aside everything hidden behind our galaxy, even if we could see the whole sky perfectly, some measurements suggest our region may be drifting in a way that the known masses cannot fully explain. Not mass we have failed to see, but motion that seems to point past everything we have mapped toward something farther out than any structure we can identify. A motion that, if it is real, reaches beyond the limits of our surveys and brushes against the foundations of our entire model of the universe. And whether that motion is real at all is one of the sharpest disagreements in cosmology today. Take a large volume of the universe, thousands of galaxies filling a sphere hundreds of millions of light-years across, and average together all of their peculiar velocities into one combined motion. That single averaged motion is called the bulk flow of the volume. It tells you whether the whole region, taken as one, is drifting in some particular direction, over and above the individual motions of the galaxies inside it. A bulk flow is not the motion of one galaxy. It is the shared, collective drift of an enormous patch of the cosmos. And the size of that drift, measured across larger and larger volumes, turns out to be one of the most revealing numbers we can ask the universe for. Our standard model of cosmology makes a firm prediction about that number. As you average over bigger and bigger volumes, the bulk flow should shrink toward zero. On small scales, Nearby masses can push a region around, but on the largest scales, the universe is very nearly the same in every direction, so the pulls from all sides increasingly cancel one another out. The bigger the volume, the more complete that cancellation should be, and the slower the collective drift should become. The theory does not just say this loosely. It predicts a specific, small size for the bulk flow at each scale, a number that should fall off in a known way as the volume grows. This is the convergence we touched on earlier, written as a precise expectation we can test. When astronomers measured the bulk flow of large volumes around us, some studies found it larger than the standard model comfortably predicts, and persisting out to greater distances than it should. The collective drift did not seem to die away as quickly as the theory required. These results are genuinely difficult to pin down, and they vary from study to study, so this is a tension rather than a settled fact. Some analyses see an unexpectedly large flow. Others, examining similar data, find everything consistent with the prediction. The disagreement itself is the current state of knowledge. Beginning around the year 2008, a group led by the astronomer Alexander Kashlinsky reported evidence for a coherent motion of galaxy clusters, all drifting together toward one direction in the sky, extending across distances so vast that nothing inside the observable universe seemed able to cause it. They called it dark flow. The claim was not simply that the bulk flow was a little too large. It was that a whole population of clusters appeared to be streaming towards something that should not exist within the universe we can see. The way they measured it reaches for one of the faintest signals in all of astronomy. When a galaxy cluster moves relative to the overall expansion, the hot gas inside it scatters the ancient background light passing through, and that scattering leaves a minuscule shift in the temperature of the background light along the cluster's direction of motion. Measure that tiny shift for one cluster, and it is buried in noise. But average it over many hundreds of clusters, and in principle their common motion should add up into something detectable, while the random noise washes out. That is the method Kashlinsky's team used to claim that clusters across enormous distances share a single drift. The signal they were chasing is so small that it sits at the very edge of what the measurement can do. If dark flow were real, the consequences would reach the foundations of cosmology. A coherent motion that cannot be produced by anything within the observable universe points to one of two unsettling possibilities. Either there is structure beyond the horizon, mass outside everything we can ever see, pulling on our region from a place permanently hidden from us. Or the flow is a remnant from before the era of inflation in the very early universe, a fossil of conditions that the standard picture says should have been smoothed away. Both would challenge the assumption that the universe is uniform on the largest scales, which is one of the load-bearing ideas the entire standard model is built on. Dark flow, if confirmed, would not be a footnote. It would be a crack in the foundation. Other teams, including those working with the detailed maps from the Planck satellite, looked for the same signal and did not find it, or found something far smaller and fully consistent with the standard model. The kinematic effect being measured is so faint that it is extraordinarily vulnerable to systematic errors, subtle contaminations that can mimic a flow where none exists. The same data, analyzed with different assumptions, has produced different answers. Most of the cosmology community currently regards the dark flow claim as unconfirmed, and many regard it as most likely an artifact of how hard the measurement is. The standard model, for now, does not need it. This disagreement persists because the measurement lives exactly at the limit of what our instruments can resolve. Both sides are doing careful, serious work. They are not arguing about sloppy data or wishful thinking. They are arguing about whether a signal far too faint to see cleanly is a real motion of the cosmos or a subtle flaw in the analysis. And at that level, honest, capable people can reach opposite conclusions from the same numbers. This is what an unresolved question in science actually looks like from the inside. Not a tidy mystery with a hidden answer, but a faint signal that two groups of careful people read in two different ways. The truthful answer is that we do not yet know whether any of these large-scale flows are real anomalies or measurement artifacts, and a story that gave you a clean resolution would be inventing one. Where the evidence currently leans, I will say plainly, the weight of it favors no anomaly. The standard model holds, the bulk flow most likely converges close to where theory predicts, and dark flow remains unconfirmed. But the question is not closed. Careful astronomers still measure these flows, still find occasional tensions, and still argue about what they mean, because the measurements are hard enough that the door cannot yet be shut. The honest position is to hold the uncertainty, not to resolve it for the comfort of a clean ending. Whatever the final verdict turns out to be, the dispute exposes a deeper limit that does not depend on who is right. Every one of these measurements, the convergence, the bulk flow, the budget of pulls and pushes, depends on the volume of the universe we have actually surveyed. And every one of them is shaped by mass that lies outside that volume, mass we account for in our equations without ever locating a single source of it. The flow within our surveyed sphere is tugged by everything beyond it, and beyond it is precisely where our data ends, which forces the last structural question we have been circling for this entire journey. How much of our map of home is built not from what we have seen, but from mass we will never actually find? The velocity field we measure inside our surveyed region is not shaped only by the mass inside that region. Mass far outside it pulls too, and that outside pull is woven into every flow line we have drawn. We have spent this whole journey tracing the pulls of things we could name, the Great Attractor, Shapley, the repelling void. But there is always more mass beyond the edge of any map, and it never stops pulling just because we stopped measuring. The flow inside our sphere carries the fingerprints of matter that sits entirely outside it, matter no survey has ever counted. The way distant mass shows itself is subtle, and it is the reason we can be fooled. A large concentration of mass lying outside our mapped region does not pull one part of our volume differently from another. It is far enough away that it pulls the entire surveyed region almost uniformly, tilting the whole flow gently in one direction at once. We measure that tilt clearly. What we cannot do is see what causes it, because the cause lies past the edge of our data, out where we have no galaxies to measure. This broad, coherent pull from beyond the boundary is what astronomers call an external tidal influence, and every large survey has to reckon with it. Because that influence is real, the reconstructions we trust must include a term for mass they never observed. When the Wiener filter builds the flow, it does not only fit the galaxies we measured. It also adds an estimate of the pull coming from beyond the surveyed boundary, a value calculated from our general model of the universe rather than from any specific galaxy anyone ever saw. Part of the map, in other words, is filled in from theory about what lies outside, not from observation of what lies inside. This is not a flaw someone forgot to fix. It is a necessary piece of the method, because ignoring the outside pull would make the map of the inside wrong. That dependence has a direct consequence for the boundary of our home. Since the flow depends partly on this pull from beyond, the boundary and the focus we drew for Laniakea depend partly on where our survey happened to stop. Extend the survey outward, bring more of that external mass inside the measured region, and the reconstructed flow shifts. When the flow shifts, the dividing surface shifts with it, and the boundary of Laniakea can move. The edge of the largest structure we belong to is set not only by the physics of where flows part, but also by the plane limit of how far we have managed to look. Our home has a border that depends in part on the reach of our instruments. This is exactly why the cosmic flows effort kept growing over the years. The catalog expanded from around 8,000 galaxies to tens of thousands, and each expansion did something specific. It pulled more of the previously external mass inside the surveyed volume, so that its pull became something we measured directly rather than something we estimated from theory. Every enlargement sharpened the map and shrank the portion that had to be assumed. But no survey can ever contain the whole universe. There is always an outside, always more mass beyond the newest boundary, always some pull that we model rather than see. The exact, true boundary of Laniakea, the perfect dividing surface, would require knowing the complete distribution of mass across a region far larger than we can ever fully survey. What we actually have is an excellent approximation whose precise edges depend on how far we have looked and on what we assumed about everything past that point. Laniakea is real. Our place within it is real. But the outermost line of its border is partly a reflection of the limits of our reach, and it will keep shifting, slightly, as those limits recede. Every limit we have met on this journey turns out to be the same limit, seen from a different side. The small residual in the motion budget that the known masses could not explain, the concentrations hidden behind our own galaxy, the disputed bulk flow that may or may not converge, and now the external pull that shapes our map from beyond its edge. Each of these is one face of a single fact. Our map of home is built partly from mass we account for in our equations without ever locating a single source of it. We can get the total pull roughly right without ever pointing to the things that cause it. On the largest scales, the statistical description of the universe is reliable. We know how mass is distributed on average, how much of it there tends to be, how it clusters, even when we cannot see any particular clump. That average knowledge lets us estimate the aggregate pull from beyond our boundary with real confidence, even while the individual sources stay invisible. The map is approximate at its edges. It is not wrong. We know our address in the universe. We simply cannot draw its outermost boundary to perfect precision, and we never will. We tend to picture a map as a record of things somebody actually saw. This one is not quite that. It is partly a record of things inferred, a careful accounting of a home whose full extent no single instrument will ever hold in view at once. The largest structure we belong to is described, in the end, by combining what we have measured with a disciplined estimate of what we have not. There is a quiet integrity in that, in a science willing to build its greatest map, while stating openly that the map's own edges rest on mass it will never find. It does not claim more than it knows, and it does not pretend the unknown away. We have drawn a border. We have named a homeland. We have claimed an address inside a structure we can never enter, never walk across, never return from, and now, we find, never fully see. The focus we fall toward is hidden. The boundary depends on our reach. The far mass that shapes us stays out of sight. And still we named it. Still we call it home. Still we say we belong to it. Which raises a question that is no longer about gravity or light at all. What does it mean to name and to belong to a home like this one? The word Laniakea comes from the Hawaiian language, and it means immense or immeasurable heaven. It was proposed by a Hawaiian language educator named Nawa'a Napoleon, and it was chosen with intention. It honors the Polynesian navigators who crossed thousands of miles of open Pacific Ocean long before any instrument existed to guide them, finding their way by the stars, the swells, and the flight of birds. There is a reason that choice fits a structure defined entirely by motion. Those navigators located themselves not by any landmark they could touch, but by reading the movement of the world around them, which is the same thing we did to find our place in the cosmos. For almost all of human history, our largest home had no name of its own, because we did not know it was one place. The pieces had names. Our own branch was the Virgo Supercluster, and the region around it was sometimes called the local Supercluster. But the whole had no name, because the whole had never been recognized as a single thing. The map drawn in the year 2014 did two things in one stroke. It revealed the structure, and it required a name for something that had never needed one before. Naming it was the moment 100,000 galaxies became, for us, a single place we could point to and speak of. Naming this structure was a strange act when you look at it directly. We have given a name, and a border, and an address to a place that no human being will ever enter. We cannot travel there. We cannot cross it. We will never stand at its center, or walk to its edge, or send anything we build to touch even its nearest part. Every ordinary reason a people has ever had for naming a place is absent here. We did not name it to claim it, to settle it, to divide it, or to take anything from it. There is nothing in Laniakea we could ever possess. That absence changes what the naming actually means. For most of human history, to name a land was often to claim it, to draw a border around it and call it ours. This naming can carry none of that, because ownership of Laniakea is not merely difficult, it is impossible in every sense. What the name gives us instead is orientation. It lets us say where we are, to locate ourselves inside something vast, to answer the oldest question a conscious being can ask, which is simply, where am I? The navigators the name honors did not own the ocean either. They used its motion to know their place in it, and that is exactly what we have done. It lets knowledge be shared. A reconstruction living inside a computer, a field of arrows and numbers, is understood by almost no one. Give the structure a name, and suddenly it can be taught, remembered, passed to a child, spoken of by people who will never run the equations themselves. The name is part of how a private result becomes a shared human possession, part of how the knowledge survives beyond the few who first assembled it. In a universe that will one day hide its own history, naming what we find is one of the ways we hold on to it. When you map a place you can never use, never reach, and never claim, every possible motive falls away except one. You are doing it in order to understand, and in order to know where you stand. That may be the purest kind of naming our species has ever done, stripped of conquest, stripped of gain, left with nothing but the wish to comprehend our own location in what exists. The people who built this map are the clearest example of that motive in practice. Hélène Courtois carried the result out of the journals and into the world, so that the rest of us could see it. Daniel Pomered turned the columns of numbers into something a person could actually look at and hold in mind. Yehuda Hoffman drew the hidden patterns out of noisy, incomplete data, including the great repelling void behind us. René Kran-Korteweg spent years in the hardest band of sky, counting galaxies no one had ever seen. And Brent Tully's rule about spinning galaxies from decades before made all the distances possible. Not one of them will ever visit the place they charted. They spent their working lives mapping a home no human can reach, and then they handed the map to everyone. Knowing our place does not make the universe ours, and it was never going to. What it does instead is quieter and, I think, more important. It changes the scale at which we see ourselves. We learn that we are on the outskirts of an unbound structure, falling toward a hidden focus, riding a flow that will not last, inside a universe that will one day hide its own history from whoever comes after us. That knowledge could make a person feel small, and it does. But it can also turn attention back toward what is near and shared, and actually within reach, with something like tenderness. We learn that Laniakea is not bound, that it is coming undone from its edges, that the vast structure we belong to is a passing pattern rather than a lasting home. That is not, in the end, a reason for despair. It is a reason to value what is close and lasting, the small bound region we actually live in, the one world beneath our feet, the people near enough to matter. When the largest thing you belong to is temporary and beyond reach, the nearest things become more precious, not less. The cosmic view does not have to shrink us. It can enlarge the care we bring back down to where we live. The facts carry their own meaning without any help from me. A structure too large to hold together, named after wayfinders, mapped by people who will never visit it, dissolving slowly in a universe that hides its own past, is already saying something plain about scale and impermanence and the value of paying attention while we can. You do not need to be told what to feel about that. You only need it laid out honestly, and then it is yours to hold however you choose. So we arrive at the most honest thing this map can offer, which is not a finished picture but a careful accounting of its own gaps. We have named our home, weighed it, bounded it, and traced the flow that carries us through it. And at nearly every step, we have run into something we could measure but not fully explain, something hidden, disputed, or beyond our reach. A truthful map of Laniakea is therefore also a truthful list of everything about it we still do not know. Before this journey can rest, we owe ourselves that list, gathered in one place, spoken plainly, without pretending any of it is settled. A truthful map of Laniakea has to include a list of everything it cannot tell us, and that list is long. This is not a confession of failure. It is what honest science looks like when you lay it out completely, with the known and the unknown side by side. But the unknowns are not all the same kind of unknown, and telling them apart matters more than any single item on the list. Some of these questions will almost certainly be answered in time. Others may never be answered at all. The difference between those two groups is the real subject of this part. The first group is made of questions that better data will most likely close. We do not yet know for certain whether the Great Attractor or the far heavier Shapley Concentration is the dominant source of our motion, because both lie in nearly the same direction and the split between them is hard to measure. We do not know how much mass hides behind the plane of our own galaxy, in the band we cannot see through, or whether another large concentration lurks there undetected. We cannot yet place the exact boundary of Laniakea, because it depends on mass beyond the edge of our survey. And we still have that small residual in our motion, the piece the known pulls and pushes did not fully account for. These are questions of precision and reach, not questions of principle. We can be reasonably confident that this first group will yield because each of these questions depends on measurements we already know how to make. We simply cannot make them well enough yet. The cosmic flow's catalogs keep growing, pulling more distant mass inside the surveyed volume. Radio and infrared surveys keep pushing deeper into the blind band, recovering galaxies that were hidden a decade ago. Every improvement sharpens the map, narrows the split between competing sources, and shrinks the unexplained remainder. This is temporary ignorance, the kind that steadily retreats as the instruments improve and the catalogs deepen. The second group is different in a way no telescope can fix. We do not know what dark energy actually is, and dark energy is the single thing that decides Laniakea's entire fate. We can measure its effects with real precision, and we still cannot say what it is or whether it will behave the same way forever. We do not know whether any of the large-scale flows people have reported reach towards something beyond the observable universe, because anything beyond that horizon is, by definition, something we can never directly check. And we cannot fully settle whether the word supercluster names a real object or only a pattern we chose to draw across a moving field, because part of that question is about our definitions, not about the sky. The nature of dark energy is a gap in fundamental physics, not a gap in any survey, and no larger catalog of galaxies will close it. A pull from beyond the cosmic horizon is permanently out of reach of direct observation, so a claim like dark flow may never be confirmed or ruled out by simply looking harder. And whether an unbound structure counts as a real thing is partly a decision about what we mean by the word, which measurement alone can never decide. This is a deeper kind of ignorance, the kind that may not shrink no matter how long or how carefully we look. We know our address in the universe with real precision, and we still cannot say for certain what kind of thing that address names, what fraction of the forces moving us we have actually located, or what the energy deciding its fate even is. We have mapped a home whose center is hidden behind our own galaxy, whose outer edge shifts with the reach of our instruments, whose entire substance is a passing motion rather than a solid structure, and whose long-term fate rests on a form of energy we can measure but not understand. All of that is true at once. All of it is our home. This one cannot, and I think it is better for refusing to. The honesty of a map is not measured only by what it draws, but by whether it marks the places it had to leave blank. The blanks on this map are not empty spaces where nothing exists. Each one is a specific question, sharply posed, waiting either for a measurement we have not yet made or for an answer that may lie forever out of reach. A map that shows you exactly where it stops seeing is worth more than one that quietly paints over the edge. Something ties all of these open questions together, and once you notice it, the whole list changes character. Every single one of them is a question about something we can never reach, never touch, and never visit, only observe from a distance and infer. The source of our pull, the mass behind the band, the disputed flow, the fate written by dark energy, all of it lies beyond any possible contact. Our ignorance about Laniakea is not carelessness or a lack of effort. It is the natural shape of trying to know a place we can only ever study from the inside, at a single instant, across distances that no signal we send will ever cross. We are asking the largest questions from the one small vantage point we were given, and some of those questions were always going to stay open. And yet there is one question that none of these instruments can touch, and it is not about Laniakea at all. Everything we have traced across this long journey, the scale that breaks the imagination, the hidden center, the dissolving edges, the flow we cannot feel, the rare window in which any of it is even visible, does not finally land out there in the dark. It lands here. In one person, awake, in the quiet, taking it in. The universe does not ask itself what any of this means. Only we do that, and only from where each of us actually sits. So the last question this journey leaves us is not what Laniakea still refuses to tell us about itself. We have that list now, honestly drawn, its blanks marked as carefully as its lines. The question that remains is quieter, and it is the one no survey and no telescope will ever answer for us. Once you truly take all of this in, the scale and the impermanence and the hidden shape of our home, what is it asking of you, the person who now knows it? We belong to a structure that is not held together by anything, that is coming apart from its edges, whose center we cannot see, whose boundary shifts with the reach of our instruments, and we ride it at a speed no nerve in the body will ever report. That is the true scale of Laniakea, and it is a great deal to carry. The question is no longer what any of it is. We have answered that as honestly as we can. The question is what it asks of a person who now knows it. Set against 100,000 galaxies and 500 million light-years, a single human life can seem to shrink toward nothing. That reaction is natural, and the scale that provokes it is real. But it is also, I think, the wrong lesson, or at least a shallow one, and it is worth saying clearly why. The size of the universe is a fact about size. It is not a fact about worth. Nothing about Laniakea being vast tells you anything at all about whether a life within it matters, because largeness and meaning were never the same measurement in the first place. To read insignificance off of scale is a simple mistake once you name it directly. A thing is not made less important by being small, any more than a mountain is made wise by being large. Worth is not a quantity of space. The mountain does not matter more than the person standing on it because it contains more atoms. So when the scale of Laniakea tempts you toward feeling that nothing you do could matter, the honest response is that the scale has no authority over that question. It is answering a question about distance and mistaking it for a question about meaning. What the knowledge actually asks, before anything else, is accuracy about where we are. For almost all of human history, we carried a wrong map. We placed the Earth at the center, then the Sun, then imagined our galaxy as most of what existed. Each of those pictures was comfortable, and each was false. We are among the first human beings who can locate ourselves correctly inside the whole structure, out on the edge of an unbound supercluster, falling toward a hidden mass in a universe that is expanding and will one day hide its own past. To take that in is to trade a comfortable wrong picture for an uncomfortable true one, and choosing the true one, even when it unsettles you, is its own quiet form of growing up. The second thing it asks is harder, and it is to hold impermanence without turning away from it. Laniakea will dissolve. The evidence of the universe's history will one day pass beyond reach. Even the bound remnant that survives is temporary, if you wait long enough. That knowledge could curdle into despair, and for some people it does. But we establish something earlier that undoes the despair if you let it. A pattern that is real right now is fully real right now, and impermanence is not the same as meaninglessness. The knowledge asks us to let something be precious and temporary at the same moment, which is not a cosmic skill at all. It is the same thing every person already does with a single day, or a life, or someone they love. The rule that governs Laniakea's fate is that only what is bound closely enough survives, while the vast and the distant are carried away, and what endures is what is near. That is not a lesson the universe is teaching us through some poetic likeness. It is the plain physics of gravity and distance, and it shows up at every scale, including the scale of a life. What we can actually keep is what is close, the people within reach, the small shared world we live on. The same physics that lets the outer galaxies slip away also tells us, without any metaphor, where to place our attention. We live in a narrow window when the universe still shows its past, when the galaxies are still visible, and the flow can still be mapped, and the beginning can still be measured. There may be minds in the deep future who can never recover any of it. To learn this now, and to carry it, and to pass it on, is to keep a memory open on behalf of those who will not be able to reach it. The knowledge asks us to be, for a little while, the witnesses. Not to own the cosmos, which we cannot, but to hold its record steady during the brief time it can still be held. When I first understood all of this, I expected to feel small, and I want to be honest that I did not. What I felt instead was located, and the difference between those two turns out to be large. Feeling small is being crushed by scale. Feeling located is knowing, at last and precisely, where you stand within it. For the whole of human history before us, no one could feel located in this way, because no one had the map. We are among the first who can, and the map does not diminish us. It answers, more completely than any generation before could, the plainest question a person can ask, which is, where am I? And the answer is not nowhere. It is here, exactly here, and now we know where here is. So gather it all together, and the demand this knowledge makes is not despair, and it is not grandiosity. Belonging to something temporary is still belonging. Standing on the outskirts of a dissolving structure is still standing somewhere, precisely somewhere, known for the first time in the history of our species. The knowledge asks three simple things of us, and none of them is heavy. It asks for attention, to where we truly are, rather than where we wished we were. It asks for honesty, about what we know and what we do not. And it asks for care, toward the near and the shared and the lasting, the only part of all this we will ever actually hold. That is the whole of it: attention, honesty, care. And every bit of that, every question, and every answer we have followed across this long night is not finally happening in a journal or a telescope or a galaxy 500 million light-years away. It is happening in you, in a single person, awake in the dark, in a body carried at the same speed and in the same direction as 100,000 galaxies, feeling perfectly still. Which brings us, at the very end, back to the smallest and most personal version of this entire story. Not the scale of Laniakea out there, but the motion of it, here, in the quiet, in you, tonight. Right now, in this room, your body is moving with everything else. The 600 kilometers per second we have talked about all night is not a fact about distant galaxies. It is a fact about you, about the bed beneath you, about the slow breath you just took. You are being carried at that speed this very moment, in a fixed direction, along with the Earth and the Sun and every star in our galaxy. There is no part of you standing outside it. Every atom in your hands is moving that way. The blood traveling through you, the air entering and leaving your lungs, the small warmth of your body against the sheets, all of it is being carried in the same direction at once, together with 100,000 galaxies you will never see. Not one piece of you is exempt from the motion. And you feel none of it. You have never felt it, not for a single second of your entire life. The stillness you feel tonight is not the absence of that motion. It is what the motion feels like from the inside. Nothing is pushing against you, because we are all falling together, the bed and the body and the galaxy as one, and falling together has always felt exactly like rest. The calm in your body right now is not a pause from the great cosmic motion. It is the great cosmic motion, felt honestly, from within. You are not separate from it, and then occasionally still. You are moving, always, and the stillness is the truest feeling that motion has. You are carrying a great deal tonight, more than almost anyone who ever lived was able to carry. You know that the pull moving us comes from a source hidden behind our own galaxy. You know that the four neighborhoods we once thought were separate were always one. You know that the whole vast structure is quietly coming undone at its edges, and that we sit near one of those edges, and that the sky itself will one day forget its own past. That is a lot to hold in one small body on one ordinary night. And now, having understood it, you are allowed to set it down. It will still be true in the morning. It does not need you to keep holding it while you sleep. There is a kind of permission hidden in that, and it is the gentlest thing this whole story has to offer. You cannot feel the motion. You cannot hurry it, or steer it, or slow it, or stop it. It does not need you to hold on. It has carried you every night of your life, whether your hands were open or closed, whether you were awake or asleep, whether you understood it or never once thought of it. Which means that tonight, of all the things you could do, you are allowed to simply let it carry you. There is nothing here to grip. Every person who has ever fallen asleep was carried by this same motion, and almost none of them knew. Every night of every life that came before you passed inside this quiet, unfelt current, unnoticed, unnamed. You are among the first who get to know exactly what is happening, and still lie here, and still rest inside it. The knowing does not have to keep you awake. It can be the thing that lets you settle, because now the stillness makes sense, and a thing that makes sense is easier to rest inside than a thing that does not. Everything vast in this story is being carried away from everything else, slowly, over spans of time too long to feel. What remains, at the end of all of it, is only what is near. And the nearest thing in the whole of Laniakea, right now, is not a hidden mass, or a distant focus, or a boundary drawn from motion. It is your own breath, moving in and out, quietly, at the center of everything you will ever actually keep. 500 million light-years of structure, 100,000 galaxies, a lifetime of measurements by people who will never visit the place they mapped, and the whole journey ends here, at the smallest and closest scale there is. One breath, then another. You do not have to answer any of the open questions to rest. The universe has carried its unanswered questions for billions of years without needing them settled, and tonight, so can you. The map is allowed to stay unfinished. The center is allowed to stay hidden. The motion is allowed to stay unfelt. None of it is waiting on you. None of it asks anything of you in this hour except that you let yourself be carried, the way you always have been, the way you always will be. Where the current is finally carrying us is not a question any of us answers by lying here and thinking about it. It is not answered in the dark at all. It is answered slowly, only by continuing, one breath and one morning and one ordinary day at a time, by waking and living and paying attention to the near and the shared and the lasting. So the last question of the night is one you are not meant to solve tonight. You are only meant to carry it gently into sleep and to wake into it tomorrow. You have done the hard part already, which was to understand. What is left now is only rest. Let the motion you cannot feel do what it has always done. Let it carry the bed and the breath and the body and the quiet, all in the same direction, all at once. I have kept you company for a long while tonight, and I am grateful you spent it here, following something this large all the way down to something this small. Thank you for staying to the end of it. Rest now. You are exactly where you are, moving with everything there is, and you are allowed to close your eyes. Good night.